Way.
Okay, thank you very much. It's a pleasure to be here, and it's as always these sort of online things. They're not quite as good. In this case, I'm also dealing with a sort of significant difference in time zones. It's about 8 o'clock in the evening over here. So welcome. Now, this talk is aimed at people who are not AI experts, and one of the issues with AI, artificial intelligence, is that the coverage in the mainstream media is often not so good and sometimes downright awful. So if you read newspapers, you may come across headlines and sentences like this, and you might be left with the impression that there is a robot apocalypse coming. In this case, reading a few more sentences, they're not coming to eliminate everything, they're just coming to take all of our jobs. Or you might have the impression that AI could potentially become billions of times smarter. And what does that mean? So in this talk, I'm going to address some of these myths of AI, things that get repeated and said in the media, but sometimes are just really wrong and also quite frustrating to people who work in the field. So hence the subtitle, what are the things that people who do work in the area of AI wish that were more broadly understood and appreciated. So some of the myths that you might have come across, often when you read newspaper articles about AI being deployed for a particular problem, you'll see phrases like the researchers developed an AI that solved the problem. And in fact, that particular framing, as we'll talk about shortly, is problematic and misleading. You might be left with the impression that the AI research community is in a unified way working on developing some sort of generic purpose, single thing, and then in fact we're not that far away from human level intelligence, and that once we get to human level intelligence, superintelligence will follow fairly shortly. And there's this idea of a singularity you may have come across. And generally, you might be left with the impression that really intelligent machines are coming soon, and that's something that we should worry about. Now, all of these things are myths, and to try and understand why they are myths and what the reality is, in this talk, I'll be tackling a number of questions. So the first question to consider is, what is AI, which will address the first myth? And also alongside that, what is the discipline of artificial intelligence, which will clarify what the AI research community is doing and to what extent it is unified. And we'll also encounter a few other myths along the way. To answer the question of how close we are to human level artificial intelligence, the question we'll consider is, how hard is it to get to human level AI? The argument about superintelligence that I'll explain later on is in fact one that rests on a whole range of assumptions. And when you start articulating and questioning those assumptions, it turns out to be quite questionable. So a lot of those assumptions really don't stand up to scrutiny. And within the discipline of AI, people are not worried about intelligent machines developing their own agendas and going out and taking over the world. We are much more worried about the potential for stupid machines making really bad decisions. And one of the key things that comes back to is that is the lack of common sense, that a computer will do what it's programmed to do, and AI stretches the envelope in terms of things like machine learning, so you don't program them explicitly to do certain things, but there's still no ability for the machine to step back and say, what am I doing? Does that even make sense? So let's start by tackling the first question. What is artificial intelligence? So artificial intelligence is basically the idea that we're programming computers to do some sort of task that we would say would require intelligence if a human did that task. The sort of awkward phrasing there about normally requiring intelligence is just an attempt to sidestep and avoid the argument about whether machines can really think or really be intelligent. In the same way that birds fly, airplanes fly, they do it differently, but they both effectively traverse and fly through the air. So similarly, and we'll see examples later on, artificial intelligence, machines doing certain tasks that we would say require intelligence. If we were to do them, they might do those tasks very differently to how a human does them, but they still can perform tasks that should require intelligence. So that's what we call AI. And it's worth observing that this idea actually changes over time. So historically, there was a time decades ago when pathfinding, working out how to get from point A to point B, that's a task that we'd say requires intelligence. These days, we have very well defined and known algorithms for solving this, and it's not really considered part of the discipline of artificial intelligence. So that's what artificial intelligence is. Now, the discipline of AI, it's a topic of study in the same way that sociology or physics are disciplines as well. And the discipline of AI is concerned with developing techniques for allowing machines to do tasks that would normally require intelligence. And one of the two key points to take away is, first of all, is AI is not developing one master algorithm or one single technique. It's in fact developing lots and lots of different techniques, and different problems require different techniques. So if you're trying to play chess, for example, there are certain techniques that get used for that. If you're trying to recognize human faces and identify them, a different set of techniques. Coming back to this idea of the phrase of NAI, a more accurate phrase would be a software system that is using some techniques that have been developed by people working in this discipline. And sometimes it might use one technique, sometimes a system might have to use multiple techniques. So to give you a sense of what the discipline of AI looks like, this is a sort of partial map of the discipline. And you'll see that it's quite diverse. It includes topics like natural language processing, techniques for manipulating text in a language like German or English, speech recognition, taking audio and getting text out of it, planning, solving problems, representing knowledge, computer vision, robotics, and machine learning. And two additional myths that are worth pointing out now. One is that AI is not a unified field. If you go to a conference in artificial intelligence, perhaps IGCAI, the top conference in the area, you'll find a lot of very specialized work where people working, say, on planning would perhaps even struggle to understand the work that's being done in neural networks. So it's a fragmented field. It's not unified. The other myth that I have to also raise at this point is, and we'll see why this is shortly, there's a tendency in recent years to conflate AI and machine learning. One example of that, I recently saw an article where they were analyzing where AI researchers would be happy to move, which countries they might prefer to work in. And what's problematic about that particular paper is they surveyed people who'd published in two particular conferences. Both conferences sit within that machine learning bubble. So the point is that the authors of that study looked at those two conferences and they said, we're representing the whole of AI with this. And of course, they're not. Machine learning is just one part of the discipline. Now, what I thought would be useful is to give a very, very quick history of the discipline. And I'm not doing this because the history in itself is that important or interesting, although I think it is, but because there are really interesting lessons that come out of it. So back in 1956 is when the discipline of AI is generally considered to have been founded and given its name. Early work in the discipline was quite optimistic. There was a real sense that AI was this problem that was really the essence of intelligence was logic and reasoning and problem solving. And if you could solve that, then everything else would be done and we'd have truly intelligent machines. And that shouldn't take too long. A lot of work was done, a lot of progress was made. And one of the key lessons that came out of that period was that reasoning alone is actually not enough. You also need knowledge. Then there was another sort of wave of development that was focused on knowledge. How do you represent knowledge? How do you reason with it? And one of the things that came out of that body of work was expert systems that can take a collection of symptoms and give a diagnosis. And again, one of the lessons that came out of that period was that reasoning and knowledge alone weren't quite enough. And for example, with robotics, it turns out to be too complex and too slow. So again, there was another wave that started to look at behavioral AI and the importance of perception and action, being able to interpret the environment and act in it. There's also been an ongoing thread about machine learning, and more recently, there's been a lot of focus on something called deep learning. So the reoccurring lesson here is that time and time again, there was optimism. There was a sense of intelligence is this, logic and reasoning say. If we solve it, it'll all be fine. will solve the whole problem. And as people learned more, there was this lesson that, oh, there's actually more to it than that. And that's a really important lesson to take away, that AI turns out to be harder than we think it is. There was optimism. It turns out that we are overly optimistic. So coming back to the more recent developments in AI, over the past decade or so, there's been a real explosion of interest and investment in AI. So you can see the level of investment really growing in this graph from 2010 to about 2015. And then from 2015 onwards, there's been continued growth. And I'll come back to why there's been this sudden growth in 2010. But one of the points to make here is that this is where we get this additional myth that AI is a very young field. There's a lot of attention that's come to the field in the last decade. And of course, the reality is that it's actually around 65 years old. Now, the reason why there's been a lot of attention to AI over the last decade, and why a couple of slides back, I sort of had machine learning, and then within that neural networks, and within that the sub area of deep learning, is that there's been a lot of effort, a lot of attention paid to deep learning. So I'm going to very briefly talk about deep learning. And again, it's not so much because I want to talk about deep learning, but because it's also a really important lesson from some of the weaknesses of deep learning. So what is deep learning? It's basically the idea that it's a form of a neural network. A neural network is a software simulation of a mathematical model that's inspired by certain aspects of the human brain. So it's not simulating a human brain. It's simulating this idea of neurons that can fire, and they're connected to other neurons, and they might trigger other neurons. So you can think of this as a network of nodes, and there's an algorithm for how nodes fire or not and affect other nodes. So it's an abstract mathematical model inspired loosely by certain characteristics of the human brain. The word deep in deep learning refers to the sort of number of layers of these simulated networks. And the reason why deep learning has attracted so much interest is that over the past decade or so, it's been able to demonstrate dramatic improvements in the ability of computers to perform certain tasks. And some of these improvements have come from developments in the techniques and algorithms. Some of them have come from computing power, really fast computers, and the availability of really large data sets. So let me give you a few quick examples. Speech recognition, this goes up to 2017, but again, you can see dramatic improvement from 2010 onwards. And just as an aside, going from 85% accuracy to 95% doesn't just mean that we're now at sort of human level performance on this task, but it also is quite significant. It means that instead of 1 in every 6 words being wrong, 1 in every 20 words is wrong. And that makes a difference to the usability. And if we look at what's happened more recently, you can see that, okay, this is actually a different task. So this is identifying objects. And again, the exact details aren't that important. The point is, for this task, again, there's been significant improvement. And for this task, computers are now able to actually outperform humans. However, these techniques are not good for everything. One example is a certain form of visual question answering that, in fact, there's been some improvement, but it's still struggling to reach human level performance. So deep learning is good for certain tasks, especially things like perception, learning simple rules, playing certain video games. It's not so good at other things, and it has 2 particular weaknesses. One is that it's a bit of an art form to engineer these deep learning neural networks to perform a certain task. There are techniques now being developed for how we can understand how these networks work, and it's difficult to provide strong guarantees that they won't break down. And you might recall earlier that I said that, remember the birds and the planes? AI can perform certain tasks, and sometimes it does it in a very different way to how we as humans would do that. And one very nice way of illustrating this is these images. So these were carefully engineered as adversarial images. So the context is there was a particular piece of software. It was trained to recognize certain images like electric guitars and starfish. Then these adversarial images were engineered, and in each of these cases, when the network was presented with one of these images, it would come back and it would say, that third one, I'm 99% sure that's a baseball. So it had a very high degree of confidence that it was recognizing a baseball in that third image. And what this really highlights is that the way that the neural network had learned to recognize baseballs was very different to how a human would do it. So if I was looking for a baseball, you'd look for something small, round, white, and perhaps with a bit of red. The network obviously learned to identify particular patterns and textures. Similarly, that electric guitar, starfish, and king penguin. And in fact, the networks can be fooled, and they can be fooled in quite dangerous ways. So that image in the middle of the slide there is a stop sign. The image on the right side, the network recognizes as being a 45 speed limit, even though, of course, it is just a slightly manipulated stop sign. So that's one of the issues with deep learning and with certain other AI techniques, is they can sometimes be operating in a very different way to a human and make mistakes that are completely alien and completely, in some cases, unexpected. So this brings us to where are we today? So today we have a broad range of techniques that have been developed by the AI research community over the many decades, and there are a whole range of tasks that we can get computers to perform effectively. So facial recognition, solving puzzles during logistics, playing certain board games at superhuman level, things like chess, checkers, more recently Go, navigating, recommending products, translating between languages reasonably well, and so on. So that hopefully addresses the first two myths. So what is AI? It's not a thing, it's just a toolbox of techniques that can be applied to solve different problems. Different techniques are used for different problems. The discipline of AI is diverse, somewhat fragmented, and it's certainly not just machine learning. And let's now turn to the next question. And the next few questions have us looking ahead into the future. So, human level AI, how close is that? Well, to answer that, we really need to step back and say, how hard is it to achieve human level artificial intelligence? Now, there's a saying that's sometimes used in research and in project management that the first 90% of the problem takes 90% of the time, and the last 10% of the problem takes the other 90% of the time. The point being that sometimes we think like we think we've tackled most of the problem, but in fact, it actually turns out there's a lot more to do than we thought. And that was certainly a recurring lesson in the discipline of AI over the decades. And if we think about, for example, self-driving cars, we have cars on the road today that can identify obstacles generally reasonably well, obey road rules, and navigate to their destination. Now, we might think, okay, we've got cars on the road, surely we can't be that far from having self-driving cars that can be fully autonomous. But it actually turns out that that last 10% is actually really quite hard and quite substantial. So let me give you an example. Suppose that you're driving along and you come around a corner, turn, and then in front of you there is a truck parked, double parked with flashing lights, and people are unloading things from the truck. What should you do? Should you wait patiently? Maybe they'll be there for quite a while. Maybe you'll annoy the people behind you. Or should you overtake, which may be illegal, it may be unsafe. So to make those sorts of decisions, it's not just about identifying obstacles and following the road. You need to have an understanding of human behavior. They're performing a task, they're unloading, how long are they likely to take? You need to have an understanding of what other drivers might expect you to do in this situation. So those sorts of things suddenly are not just about the hard problem of identifying obstacles in a complex scene and following a road, they're about the much harder problem of understanding human norms, human behaviors, and when it's appropriate to perhaps break the law, to overtake illegally. So to understand how close we are to achieving things like self-driving cars, let alone full-blown general purpose human level AI, we need to have an understanding of how hard these tasks are to do. Another example is real-time audio translation. Again, we have tools today that can do that, but doing it really well, in fact, turns out to not just require matching words and matching sentences and learning from the vast amount of text that's online, but it actually requires understanding of human culture, human history, and even perhaps human emotion. So if you have a piece of text and you want to translate it reliably and capture what it's saying for an audience in a different language, you need to understand what it actually means in the original language, in the original social context, cultural context, and then replicate that. So let me give you an example of that. I suspect that this conference has a lot of German speakers in the audience. So there's an original piece of text there in German and 2 translations, one by machine, one by a human. I'll give you a few seconds to read that. So hopefully you can see fairly clearly which one's the human translation. It's the middle paragraph. But the point here is that the bottom translation is pretty good, but it loses meaning in a number of places, and some of that's fairly subtle. So for example, that very last sentence, and scientists did not question anyway, the original text is talking about female scholars, which in fact is crucial for the meaning of what it's saying. So that's an example where translation can sometimes get things wrong because it's missing the context. And of course, to translate some of the concepts from German, sometimes you have to actually explain them because they're not known. So for example, the idea of what is a professor in the German system might be different to what a professor is, say, in the North American academic system. So to get a sense of how close we are to human level AI, we need to understand what things are hard, what things are easy, and how hard is full-blown human level intelligence. So let me give you a few examples of tasks and how easy and hard they are. Logical reasoning, something that was tackled back at the dawn of the discipline, turns out to be easy, relatively easy to formalize and program. The but there is, it doesn't actually scale up to larger problems. You have combinatorial explosion. On the other hand, physical sensing and locomotion, perceiving an environment like robots have to do and navigating around it, actually turns out to be quite hard. Understanding humans, relating to them is very hard. And common sense, that sort of body of knowledge that allows me to know that if I take an egg and let go, it will fall, it will break, and it will make a mess. That's also very, very hard. So one point here is that the tasks vary from easy to sometimes very hard or even extremely hard. And I'll come back to the other point a bit later on, that sometimes working out which is not at all obvious. So I want to quickly digress to talk about creativity, because that's also something that you'll come across in the media. Can computers be creative? Can they create new things? So let's give the example of composing music. Now, in fact, this is something that I do as a hobby, so I do feel that I can talk about this. How hard would it be to get a computer to compose music? Well, like a lot of questions, the answer is it depends. Creating a new piece of music is actually really easy if you're just generating random notes. And if you set it up with, say, a nice pentatonic scale, it'll probably sound listenable and it may actually work. It would be new, but it's not particularly necessarily well structured. Creating a piece of music that follows appropriate musical structures, perhaps chorus and verse, and with the appropriate amount of repetition, that's harder, but it's not that incredibly hard. What is hard, though, is having the computer be able to take something that is generated and assess whether it is actually a good piece of music or not. And for example, taking a poem, reading it, assessing the mood of the poem and setting it in a way that reinforces that mood, that's very, very hard. And it's probably what we call AI complete. In other words, to do that, you probably need to have a computer system that is equivalent to a human, that can understand the meaning of text, understand emotions, and try and replicate them. And before I move on, one thing that appears a lot in the media is stories of the form, here's a piece of music, of art, or of text that a computer created. And if you delve into the article or dig into the backstory, almost invariably what's really going on is humans played a role in setting up the computer, deciding, for example, what scales to use, what musical structure. So it's not just the computer creating things completely on its own from a blank slate, but then they'll hit the button and generate a number of things, and a human will then look at them and go, oh, that one's a bit boring, but that one looks cool, I'll select that one. So really, a better way of framing this, hey, computer created a new piece of art, is we set it up so that it has the background to do that. We hit the button and then a human came along and did the which one of these is good. So selected by a human is actually quite crucial. So the key points in terms of this difficulty thing is that some things are easy, some are hard, and some are very, very hard. So the range of difficulty is quite a wide one. Some of these things, like how can you get a computer to listen to music and say, yes, that's good, that's not so good, that's really difficult. The other key thing, and I've hinted at this already, is that it's not easy to know what things are easy and what things are hard. And back at the dawn of AI, the focus was on logical reasoning because the feeling was that's the hardest thing. All this perception stuff, that's fairly easy. And what that reflected was a human-centric assessment. We as humans find perception fairly easy to do. We're well designed to do that, if you would. We find navigating around a room fairly easy to do. Logical puzzles, quite challenging. For computers, it's actually the other way around. Just because we humans find navigating and perceiving things easy doesn't mean it really is easy. It just means we're really good at it. Conversely, just because we find logical puzzles hard doesn't mean it's, or mathematics or algebra, doesn't mean it's really hard. It just means that it's not a natural thing for humans to do. So our assessment of what's easy and what's hard is colored by our own view of what's easy or hard for us. And that sometimes misleads us to think, well, this is a really hard problem, whereas in fact, it's not. The really hard problem might be something different. So coming to human level general intelligence, two bits of terminology. So weak or narrow AI is what I talked about in the very early slide, getting a computer to do something that if a human would be to perform that particular task, would say it required intelligence. That's something that clearly is being done. There are a whole range of tasks that computers perform and has been for a while, but it's narrow. So a computer program that's been developed to play chess, it's not going to be recognizing faces, not at the very least without substantial reconfiguration and training. Strong AI is general purpose intelligence, a single system that can do anything that a human could do. And that's something that is not here. We don't have any examples of that, but we know that it's possible because we humans are examples of that. On that scale of easy, hard, very hard, that's something that's extremely hard. And I'll come back to what I mean by extremely hard a bit shortly. Now, how do we know, by the way, if human intelligence has been achieved? There's the idea of the Turing test, that you can put a human in a room, put a computer in a room, have a conversation with each of them through a typewriter. And if you can't reliably pick which one's the human and which one's the computer, then the computer has passed the test. And the key point is that it's really meant as a sort of really hard task because you can ask all sorts of questions. You could say, make up a poem for me, or here are 3 jokes, which one is actually funny? Here's a recent transcript from a cutting-edge AI system. And I'll give you a few seconds to read in a second, but one of the points here is that modern day natural language processing techniques can string together sentences that are grammatically correct and flow in terms of topic, and that's really impressive. What they don't have, though, is an actual understanding of what's being asked that allows them to provide appropriate answers. So have a quick read through that. Okay, so as you can see, it's sensible grammatically, the topic flows reasonably well, but in terms of the answers being sensible, they're clearly not. And I think this particular system is clearly not passing the Turing test. So, coming back to how hard is it to achieve human level AI? So there's a lot on this slide. Let me quickly talk through it. So the big chart in the middle there comes from a survey that Professor Toby Walsh did. And what he did is he went out to a whole bunch of people and asked them, by what year do you think there will be a 50% chance that we have human level machine intelligence? And those curves are cumulative. So the top curve there says that by the year 2040, roughly 50% of the respondents thought that by 2040 or earlier, there'd be a 50% chance of human level machine intelligence. The key finding here, though, is that that top yellow line is asking the general public. When Toby asked people who worked in the discipline of AI, they were significantly more pessimistic. They expected slower progress. So the point by which the general public thinks 50%, well, half of the general public thinks by then 50% chance of machine achieving human level intelligence is about 2040. For people who work in the discipline of AI, that's more like 2062. And in fact, Toby went on to use that as part of the title for his book that talks about AI. So the point here is that experts, the ones who do understand the difficulty of the problem, are more pessimistic. They're saying, no, it's actually really hard. It'll take us longer. It's also worth noting that, in fact, most AI researchers, if you go to conferences on AI and look at what they're working on, they're not trying to achieve general purpose human level intelligence. The vast amount of work in the discipline is focused on improving particular techniques for solving particular narrow problems. And that's not a criticism. I mean, solving narrow problems can be enormously powerful and enormously useful. If you can allocate resources more efficiently across the supply chain, say, that can have enormous benefits. If you can predict the outcome of chemical interactions and develop new drugs, again, that can be huge. So AI is generally, especially with the recent boom, it's making an enormous difference and is expected to make an even bigger difference to human well-being, to economic and other forms of well-being. So most AI researchers are not even looking at trying to achieve general purpose human level intelligence. And furthermore, getting from where we are today to general purpose human level machine intelligence, the current approaches and techniques that we have, it's not even clear that they're adequate. It's not just a matter of taking all the toolbox of techniques that we have and extending them and building on them incrementally. We need potentially completely different new techniques, and we don't know what they are. Now, it's possible that tomorrow somebody will wake up and have this brilliant vision and say, if we do things this way, it pulls everything together and suddenly that solves the problem. I think it's fair to say that most people in the field don't expect that there's a sort of single easy idea that will solve AI. So it's really hard. We're not expecting it to be solved anytime soon, and we're not in fact really sure how you would go about a path towards human level machine intelligence. So that's the human level AI. It's not closed and it's extremely hard. The next headline that we actually started with was this idea that AI might potentially be billions of times smarter than humans. So the person they interviewed actually, I think, said it could be. The headline, of course, made that more certain and stronger by saying it will be billions of times smarter than humans. Now, this is a good time to bring a quote from Professor Michael Wooldridge, who is very much an AI researcher, a very highly regarded one. And he writes that it is a source of great personal frustration to him that the press are happy to give airtime to views on AI that he considers to be ill-informed at best and lunatic fringe at worst. So one crucial takeaway message that I would really like to stress when you're reading articles in the media where the reporter has interviewed someone about artificial intelligence, always ask the question, who have they interviewed and what is their expertise? And if it's somebody talking about superintelligence, do they actually have expertise in AI, or are they someone with expertise in a different domain? Maybe they're a physicist or a philosopher or a successful entrepreneur. And just to highlight how ridiculous it is that we're asking, say, entrepreneurs about AI, if we had an article that was about the prospects for curing cancer, and there were comments there from an entrepreneur or from a philosopher about, well, we're progressing and we're expecting to have a cure for all forms of cancer in the next 5 years, I think we'd be extremely skeptical and we'd be saying, well, what do the medical researchers say? Because we recognize that cancer is a complicated collection of diseases and that you really do need expertise to talk about it sensibly. And that's also true for AI. As you might guess, the quote there that AI can be billions times smarter than humans is not coming from somebody who has relevant expertise. So, billions of times smarter, superintelligence, what are we talking about? So quick definition, superintelligence is any intellect that greatly exceeds the cognitive performance of humans in virtually all domains of interest. And when you start reading about that, one of the other ideas that comes up is this idea of a singularity, which is a hand-wavy argument that when we develop human-level general-purpose intelligence, which remember is not expected to be anytime soon, what happens then? Well, the machines are like general purpose. So what can they do? They can design new machines that are even better. And computers are getting faster as well. So they'll design faster, better machines. Those machines will design even better machines. And you get this self-improvement kicking off that grows exponentially. So before you know it, we have machines that are billions of times smarter than humans. So that's the hand-wavy singularity argument for why superintelligence is going to happen quite soon and very quickly. Now, like a lot of hand-wavy arguments, when you dig into it, it rests on a number of assumptions, and these assumptions are, at the very least, questionable. So, first of all, there's the assumption that you can draw this graph with intelligence as one axis and time as the other. So intelligence is a single dimensional thing. It also assumes that there's no limit to intelligence, that you can have such a thing as billions of times faster. There's a bit of an assumption that faster is smarter. So as computers get faster and faster, they will also get smarter. And of course, the key assumption is that self-improvement is possible indefinitely, and that it kicks in at more or less human level. So if we had a general purpose human level AI, that's when it could start doing significant self-improvement and kickstart this whole process. And none of these assumptions actually really stand up to scrutiny. So we know that intelligence is not one-dimensional. I'm sure you can think of people who are really good at certain types of tasks and much less good at other types of tasks. And we also have no reason to assume that there are no limits to intelligence. There are limits to everything in the physical world. The speed of light is a relevant limit. So it's highly unlikely that it's even possible to have something that's billions of times smarter than a human. We don't know where the limit is. It may be that the limit is sort of 10 times smarter, whatever that even means. It might be that 2 or 3 times smarter is about the limit. The assumption that faster equals smarter can easily be dispelled by imagining a dog that can think 5 times as fast as a normal dog. They may be really good at running around and finding things, but they're not going to be playing chess. So speed is not necessarily intelligence. And finally, in terms of self-improvement, we've actually had decades of humans, in fact, really smart humans, working on AI. And we're not even close to human-level AI. So if we suddenly had human-level AI magically appear today, it's quite possible that that human-level AI would be working for another 60 years in order to even substantially improve itself. Human-level AI is really, really hard, and that's something that people outside the field don't really appreciate. So if I can summarize this, again, quoting Michael Wooldridge in his book, he has a section titled "The Singularity is Bullshit," which I think summarizes quite nicely his perspective. So we've seen that human-level AI is not something that we need to worry about in the near future. The superintelligence is not something that we really need to worry about. However, AI does raise a number of concerns. So the real concerns are not superintelligence, they're things like algorithmic bias, unemployment, autonomous weapons, and a whole bunch of other things. Diversity in the discipline of AI is still quite strongly male-dominated and not ethnically diverse. Fake news, facial recognition, a whole bunch of ways in which AI provides tools, and then those tools can be abused or misused. Now, I don't have a lot of time to talk about all of these, but I think it is useful to very quickly touch on a few of them just to give you a sense of what's the issue and what's the concern. And I apologize if these are things you've already come across. So algorithmic bias, how can an algorithm be biased? Can an algorithm be racist or sexist? Well, if the algorithm is learning from data, then it can certainly pick up all sorts of biases from the underlying data. So let me give an example to illustrate. This is a passage, a collection of sentences in Hungarian. Why Hungarian? Because Hungarian doesn't have a notion of gender. So you'll see all of these start with a O, szép, or okos, and so on. I apologize for my pronunciation. If you run this sentence through Google Translate, you get the following result. She's beautiful, he is clever. She's a cleaner, he's a politician. He makes a lot of money, he's a professor, she's an assistant. What's going on here is that Google Translate relies and learns from the vast body of text that's out there. And statistically speaking, you are much more likely to see he is a politician than she's a politician. So the translation reflects the biases that exist in written text, which in turn reflect the historical biases that exist in society. Most countries, if you look at the collection of politicians, there are more male politicians than female politicians. So if I tell you that someone is a politician, statistically speaking, it may be the right thing to sort of say, well, if I have to pick between he or she, maybe I'll pick a he. So the point here is that biases can be picked up. Now, the right thing, of course, to do is simply to not assume, and to give Google a bit of credit. If you just take the first one and run it through Google Translate, it will come back and say, hey, Hungarian doesn't specify gender. I could translate this in 2 different ways. Which one do you want? There is room for improvement of the translation, but the point is that algorithms can pick up a wide range of biases from the underlying data. And even worse, if algorithms are used in certain ways, that can lead to negative loops. A simple example there is, imagine using crime statistics to decide where do you allocate police patrols. Well, where would you put them? Where there's more crime reported. But of course, the more police you put into an area, the more likely there is to be even more crime reported, because that area is under more scrutiny. Conversely, if there's an area that historically maybe hasn't had very much crime reported and you under patrol that area, you're even less likely to find more crime there. So that sort of reinforces with a negative feedback loop that sort of just strengthens the bias. And the challenge with algorithmic bias is that it's not easy to fix. Sometimes you can remove information from input data, but there are still proxies for that data. So for example, if you have a system that's trying to recommend loans or insurance, you might say, well, we don't want to tell this system about the race or the ethnicity of the people applying, because that should make a difference. But in fact, machine learning might find that there are other things that you can use as a proxy. So for example, in the US, postcode is a pretty good proxy for ethnic identification. And probably the best fix for algorithmic bias is to be aware that it can happen, be aware that it's not that easy to fix, and therefore it's a question of where do you use machine learning, in what ways, how much oversight is there, and what ability is there to challenge decisions. Another thing that's important is being able to explain why a system made certain decisions or recommendations, so you can understand what factors fed into it. The second issue is AI-created unemployment. And there are 2 arguments that I made in this space. One of them is an abstract economics argument, which is, yeah, we've heard this all before and it hasn't happened. So we've had previous waves of automation and there's not been mass unemployment. And the high-level economic argument is that more automation results in more wealth, because it's production of goods and services becomes more efficient. And if there's more wealth, that means there's more demand for goods and services. And that demand then translates into actually more jobs for creating those goods and services. But of course, one thing that argument doesn't consider is the wealth distribution. And if automation means that wealth gets disproportionately concentrated into certain subgroups of the population, that can be unhealthy for the society, and it can undermine this argument. So if instead of having a whole collection of people who are reasonably affluent and spend money, they end up becoming poorer, and a tiny sliver of the population gets a lot of money, they won't spend as much. The counter argument is, hang on, but this time it might be different. If we can potentially automate all the tasks that a human might do, then why would you employ a human? Machines are going to be more reliable. And the analogy there is sort of peak horse, the idea that at some point in history, there were a lot of horses pulling around things, and once the internal combustion engine, cars and so on came around, those jobs disappeared, and we now have much, much fewer horses. However, as we know, human-level AI is not that close, and there are a few factors that sort of mitigate this potential for widespread unemployment. One is that automation is most likely affecting parts of jobs, not whole jobs. And the other one is that if it occurs over a reasonably long time period, then there is naturally adaptation that occurs in the job market. Now, of course, just because something is possible to be automated doesn't mean that it's financially viable, or it may not be acceptable to automate it. There are some things where we'd really want humans to do, even if a robot could potentially do it. For example, I would probably feel uncomfortable having a robot cut my hair. It's often pointed out that technology doesn't just destroy certain jobs, it also creates new jobs. So the bottom line in this sort of unemployment issue is that in fact the jury is still out. We don't know how this will play out. It may be that certain occupations do get replaced relatively quickly. So driving might be an example of that, where if self-driving trucks do take to the highways in the next 5-10 years, that may result in significant unemployment in that sector. But it's too early to tell. And there are, of course, things that computers don't do well because they're really challenging to do well, and they're the things where humans are still going to be most needed. So abstraction and deep reasoning, being able to read something and really understand it, creativity, which we've talked about earlier, and dealing with people, communicating effectively, understanding people, and having emotional intelligence. The third issue that I wanted to flag, which is a sort of challenge and threat from AI, is autonomous weapons, sometimes known as killer robots. Now, almost all media articles about this topic, unfortunately, tend to have a picture of the robot from the Terminator movies, and that's misleading because that's not what we're talking about. We're not talking about highly sophisticated devices that can plan their agendas and have sophisticated goals or are humanoid. We're talking about something much, much simpler that does not require strong AI and can be done today. So imagine a small drone with sensors and cameras. It can navigate, it can recognize faces, we know how to do that, and it can identify people and fly up to them and then detonate. That stuff can be done potentially today, and if it is done, it's incredibly dangerous. Pardon me. There's a video that's well worth watching that's sort of, it's done like a short documentary. It talks about how this plays out. But basically the key concerns with this technology is that it's a weapon of mass destruction. Technology tends to become cheaper over time, and if this stuff gets developed and starts getting deployed, it'll make its way into the black market. It will become widely available. So a country or even an organization could potentially buy up a whole pile of these things. So it's a weapon of mass destruction, and it's a precision weapon. If you detonate a bomb, you're affecting everyone in that area. If you send a swarm of these things into a university or a senate, you can set them up to identify particular people based on who those people are, based on their ethnicity, based on what Facebook groups they belong to. So it's a precise weapon, and it's an amplifier. I said earlier, countries could have a lot of these things. Individuals could deploy them, and that's the really scary thing. It's not that nation states might start using these in far-off wars. It's that individuals will start using them as weapons of terror. And of course, nation states could also use them as weapons of oppression against their own people. So that's a really big concern, and there's a move to try and get these things preemptively banned before they get developed and become widespread. And there are a whole bunch of other issues as well, which I don't really have that much time to talk about, and I suspect others will talk about them as well. So things like accountability, responsibility, robustness, and transparency. Can we understand why a particular piece of technology is doing what it's doing? Can we then have some way of saying, well, it's doing something wrong, who's responsible for that and who becomes accountable if it's a problem? And are these machines going to be reliable? The bottom line is that AI is a powerful technology, collection of techniques, and we need to use it wisely and develop our policies around it carefully. And one of the things that's crucial in doing that is that that's not something for technologists to come along and say, this is how we should be using AI. This is a question for society, for the philosophers, the sociologists, the politicians, and for everyone. But in order to have a good, sensible discussion around AI and its uses, it needs to be founded in accurate information. So some of these myths are problematic because they take us away from where the issues really are, and they lead to unfounded discussions. So myths like there is such a thing as an AI, and the AI community is working in a unified way to develop an AI, and it's a really young field, but human level AI is really close, and then we'll have superintelligence and we have to worry about that. That's not helpful. And as we saw, AI, which is much more than just machine learning, is in fact diverse, specialized. It's a discipline providing a toolbox of techniques that's been around for 65 years or so, and that human level AI is not something that we believe is imminent. And the real worry is stupid machines doing things that in a bad way because they just don't know better, and misuse of AI. And that's something that is up to all of us to be part of the conversation and to develop appropriate responses, practices, and legislation. So I'll finish there. I should have also said at the outset, I'm very happy to share my slides, and I've got a few recommended books and articles there as well. So thank you very much. I'm happy to take questions.
Thank you so much for that enlightening talk on kind of what AI means to a different field, bringing that perspective to this interdisciplinary audience. I think that was very helpful to clarify the notion of AI. And with that, I would just segue into the first question. Do you think we need to reformulate the notion of AI to move it away from this discipline name and capture the meaningful notion of intelligence?
Do you mean sort of the name of the discipline?
Yes, I think what the question means is kind of right now we use AI to capture this wide range of discipline, the slide you had in the beginning. So should we then actually try to reformulate that concept and apply it, to mean actually, intelligent behavior, what is meant like compared to human behavior? So we would just use, machine learning or algorithms instead of AI.
Yeah, I mean, the other term that gets used sometimes is machine intelligence, which is pretty close. I think the term AI I don't see as problematic because, I mean, the key thing is that we are trying to develop techniques for machines to be able to exhibit intelligence, and it's narrow intelligence, and perhaps we could try and communicate that better. But it is machines. It is, I mean, maybe we could use machine intelligence than artificial intelligence. But it's still sort of, how do we get machines to behave in ways that are intelligent on particular tasks?
Yeah, thank you. The next question asks, what's harder, beating a human in a computer game or collaborating with a human in a computer game?
I would say collaborating is harder because to do collaboration effectively, you have to understand what the other person might be doing and perhaps anticipate what they're doing. And conversely, for a human to be able to collaborate with a machine, the human needs to be able to understand what the machine is doing, which either means the machine has to have some way of communicating things like what it's about to do and why. And also it may mean that you want the machine to behave in a human-like way. So it doesn't behave in a really odd way. And for example, one of the things that's been observed about machines playing chess or machines playing Go is they sometimes play moves that you think that's a really weird move. No human would make that. It might be a really good move, but it's a non-human-like move. And if you're doing collaborative things, that's not really helpful. If you're trying to work with a team and your teammate does something really weird, it might be the right thing, but if there's no explanation or communication to go with that, it can lead to misunderstandings.
Yeah, wonderful. Thank you. I remember this weird Go move the system played, and then everyone was puzzled. It's like, why did it move? So I can relate. The next question is linked on, was connected to it. I think it asks, why is it important to understand how hard a problem is to solve it sufficiently? We don't need to understand what 8% of the work looks like to get started and achieve the work.
Why it's useful to understand how hard something is to get a sense of when do you anticipate it might be solved. So you can certainly get started. I mean, if something's too hard, then you might want to think, really, do I want to tackle this? Am I going to get anywhere in the next 10 years? And if you're happy to invest 10 years and not have much to show for it, or incremental progress, that might be fine. But in terms of saying, right, we're going to have this problem solved in 5 years, or we're going to have this problem solved in 20 years, that's where it matters, about that expectation. And a good example of that is self-driving cars, where again, companies that are developing these things have put out a whole sequence of statements over the years that have been quite optimistic and that have been questioned by people within the field. There was one particularly well-known statement that was made about there will be this many cars by the end of this year, and a couple of well-known figures in the AI community said, if that's true, we will personally eat those cars. And of course, they didn't have to eat any cars.
Okay, that would be quite interesting to see. Fair enough. Then the next question asks, okay, should AI-powered systems be unconditionally benevolent, cooperative, and submissive?
So the issue with that is that, first of all, it's not clear how you would define benevolent, because often in the real world you get trade-offs. So if you have a situation where an AI system has to behave in a way that it's not going to make everyone happy, so one person prefers option A, another person prefers option B, what is the benevolent option? So it comes back also to Asimov's laws, which sound really nice on paper, but they just are not implementable. And there's two reasons why they're not implementable. One is that they require a lot of being able to reason and interpret situations and common sense that we don't have. We don't even know how to begin to get the machines to do that. And the other issue is it assumes that you can anticipate the future and predict forward and work out what will happen. And machines are not, AI is not magic. It can't foresee the future. So similar with self-driving cars and the trolley problem, there's a whole body of work that says, well, what should a car do if it sort of sees a pedestrian, it has the option of crashing or veering and hitting an elderly grandmother with a cat? And you can set up all sorts of trade-offs and try and tease out what humans' ethical decision-making. A car in practice is not going to have that degree of perception to identify all the things or the time to really think about it. It's just going to, if it suddenly sees an obstacle, you slam off the brakes. That's about all you can do. So.